architecture. And you need to port the different tools that you're going to use as well. So, it's all very well trying to get your kernel to run, but if your C compiler can't actually compile code for that processor, then you've got to get that to work first. So in reality, you've got to get a lot of things done before you can even get Linux up and running on a new kind of chip. Fortunately, that doesn't happen very often. As I said at the beginning, there are already 20 architectures supported by Linux, and that's after 17 years, 16 years, whatever, a long time in the development of Linux for us to get to the point where we have 20 architectures supported. Yeah?
You said that the Intel A32 includes not just the 86, but the AMD 8664 and the variant.
No, I didn't say that. I said...
You said not?
No, yeah.
Okay.
Yeah.
You didn't mean to include them?
No.
I was wondering... Okay.
Sorry, yeah, when I say...
Power and PowerPC are the same instruction set architecture, essentially. They're two families within one ISA, so I'm wondering why are they separate?
Why am I separating them? Okay, so a bit of history. See, I knew you were going to ask that somehow. Here is the original PowerPC architecture manual. You can't buy these anymore. This took me 2 years to get hold of because I really like reading IBM documentation. And what actually happened with the PowerPC was that they needed to come up with something, they being the AIM Alliance, Apple, IBM, Motorola. They needed to work on something. IBM already had the power, so they got the power. Let's do something with it. Let's make a new kind of chip. Let's make it cheaper. Let's make something that's easier to mass produce for consumer use. That's maybe not as powerful as the big mighty power processor. So they reduced it and they called it the PowerPC. There's compatibility there. Some of the early chips, the 601 especially, was actually a modified power. Okay, but strictly speaking, they are two separate ISA, two separate instruction set architectures. Okay, you've got power and you've got PowerPC. There's a what's the term I'm thinking of? An intersection of the two. So they have a kind of common subset, if you like, of instructions that are shared between them both. But that's not, yeah.
Hey, I was just going to say, in one consulting job that I had to port an application from a very old version of AIX to a slightly less old version of AIX. And if you ever have to do that, you'll find out why Power and PowerPC are listed differently. Just the compiler options, to figure out the right compiler options to go from one to the other was a horror.
Fundamentally, you could write a very simple piece of assembly code that would work on some Power and PowerPC machines. But I do list them separately because they both extend the core ISA in different ways. They have their own instruction sets. But you're right in saying they share a common history, common ancestry. And the history of PowerPC is especially interesting if you're into that kind of thing. Again, there's a great book here and there's some great resources online that go into that in more detail.
So you're going to call the various flavors of 86 other architectures as well then?
In that sense, I'm going to say the x86-64, I'm going to say that's a different architecture because we've made a lot of modifications there, so we can have code that runs on that and does not run on a regular kind of x86 processor. Yeah, there's again, I'm not an x86 person generally. I try to avoid it. And the exact way that's handled in Linux has kind of always been a special case because that's where it originally came from. So a lot of the more recent ports have been much cleaner, much more separated. We are at the point where, so the PPC-64 and PPC-32, PowerPC, regular PowerPC and the higher end PowerPC-64, essentially one set of code was copied, renamed, and a few changes were made. That might not be the best way of doing it because there are a lot of things that they could share and don't. They just have straight copies of the same file.
Which is bugs they share.
They shared bugs originally, and now they diverge in their sharing of bugs. Some new bugs come up here, and some new bugs come up there. So yeah, there are ways to do this and ways not to do this as well. And I guess by spending way too much time going through the architecture code in the kernel, like I've done, you can discover these little amusing anecdotes. So anyway, the point being, it's very difficult to get Linux working on a new architecture. It's not something we do every day. They don't tend to come out every day. And when they do, a lot of work is involved. Okay, so architectural differences. Let's just give some examples of architectural differences. How do we define memory in our machine? Since I used memory examples earlier, I'm going to use another one. How do we define virtual memory? So we all know that, or most of us, I guess, in this room know that on Linux machines and Unix machines, and in fact Windows machines, and pretty much every other regular kind of computing device these days, memory in the machine is abstracted. We have this concept of virtual memory. We can use disk space to augment our memory and give us effectively more memory than we have in our machine otherwise. We have this concept of virtual memory. And that relies on various support from the hardware in our machine. It doesn't just magically happen. Okay, there has to be a way for the machine to execute instructions and to know, okay, I'm going to go ahead and access some data in a memory address, except that's not really where it is, it's really somewhere else, but I need to figure out where to go from the virtual memory to the physical memory address of that piece of data. So how that's implemented varies from one type of architecture to the next. Why does it differ? Because it does. Which way's up? Well, we've heard we've probably heard the Indian story. For those that haven't, the story Gulliver's Travels, where you have the Indian people who constantly debate about which way up an egg should be when you are eating it. The name Indian was taken from that context and used to describe machines where they order numbers in memory differently, again, for seemingly arbitrary reasons. But people get very attached to the way their machine does things. Intel machines, a little Indian. People get very attached to Intel's way of doing things. IBM machines tend to be big Indian. PowerPC can be both, depending on a configuration option in the processor when I turn it on. It's all very exciting. People get very worked up about it. So there are differences because there always are differences between two different architectures. How does Linux implement virtual memory? Well, Linux has its own implementation, fundamentally very similar to that that's used in the Intel architectures themselves, because that's where it came from. That's where Linux was first running, so that's where the implementation has come from. What it does mean is that if you're on an Intel machine, if you're on a regular x86 computer and you are using virtual memory, it's a lot easier for implementation within the kernel to function. If you're on a more interesting, huge IBM power server, then a lot more kind of hoop jumping has to happen within the kernel in order to adapt how Linux does things for how the hardware does things. But the fundamental point here is there are differences between one architecture and the next. If you like diagrams, here's another one. So again, if I just take the notion that in my machine I have virtual memory, I have this concept of being able to have programs see memory however I like, the reality can be completely different. So here's my program, nice ordered memory. I can use memory address 1 followed by memory address 2 and so on. It looks all nice and ordered. In reality, it's all over the place physically in my machine. Some of it's not even there. This one of these pages here, one of these pieces of memory in my program may not actually physically be loaded right now. And when I try to use it, I'm going to get a fault, a page fault. My machine's going to have to go, my kernel's going to have to go and say, okay, this data's not there right now. It must be on disk. Pull it in, swap it in. Let's pull that data in again. Okay, so we've got all this kind of stuff going on. The kernel has to worry about that. Implementation, again, varies. Intel do things one way. They have a concept of this tree hierarchy here, where I have an address in my program, a piece of data. I want to go and access that memory address. And when I try to access it, my processor knows, okay, I'm going to take my processor register, find out where my table describing memory is, find out where this memory address physically is really located by following through a bunch of tables. Or I might have something completely different. Might have a PowerPC 405, like this one, where memory is, there is no hardware support for virtual memory, where what happens is, every time I try to access a piece of data, processor says, what do you want me to do? And the kernel says, oh, okay, I'll work it out for you, and I'll tell you where that really is located. So sometimes it can even all happen in software. The point being, wildly different implementations to support something that we all take for granted. We all take for granted the concept that I run my program, it accesses data. Okay? It's all just data, it's just ones and zeros. I don't really care how that happens. Architecturally, it might be very different from one type of machine to the next. It's just a concept. Everyone does it differently. Some people use giant tables. Some people do all kinds of weird things. It's just a concept. The kernel's job is to take this and wrap it up and abstract it and make it nice and the same for everyone. But it's an architectural difference. I have these differences between different kinds of processor. There's nothing I can do about it. Okay. So we accept that for a second. What else do we need to worry about? Well, if I'm working at the kind of basic level of different architectures, I need tools that are able to build for a specific architecture. I need to be able to compile code for my particular Intel family of processor. I need to be able to compile code for my PowerPC, for my ARM, for my Blackfin 537, I think that one is. You know, whatever my different kinds of processor family are, I need to have tools that can compile code for it. I need to have a very, very complex kernel build system. If you go through the Linux kernel build system, it will scare you because it's very complicated. Okay? They do a lot of hackery. They use these tools in very interesting ways. They weren't really designed to be used in when they build up the kernel. Partly because you know, you don't just compile the kernel. It's not just a regular C program. I have to compile the kernel, and I have to instruct my tools to physically place pieces of code in specific memory locations. So when they load onto my computer, they're going to be at physical memory locations that are mandated by my hardware vendor. Okay? My hardware vendor tells me, if I want to write code for a PowerPC, if I want to write a kernel for a PowerPC processor, I have to arrange it so that some core pieces of code that it expects to find are at specific addresses in memory. Okay? Not like building a regular program. I have to use special tools. I have to use special linker scripts that tell the GNU linker, okay, this is how you're going to put it together. Try running a tool called, just one second, I'll come to the question. Try running a tool called object dump, obj dump, on your Linux kernel. Okay, and what you'll find, you want to run it on the VM Linux file, which is produced in the top level of your Linux kernel sources when you build the kernel. It's a huge file. The object dump is even larger, and it will show you what the compiled code looks like. The point being that it's all neatly arranged with certain addresses being well known. For example, you see the top one there, C followed by zeros, 12 gig. That is the standard address at which my kernel starts. I just happen to know that. That's one of the standard things. So you can go through, you can look at these tools, and you can see how the different parts of the code have been laid out in the binary itself, following conventions. You had a question?
Yes. What do you mean by the third bullet there?
check out dummy build. Yeah, I explaining that